Hello everyone, now we will present our final project. Our project title is Transaction of Sequence-to-Sequence Network and Attention. Our group is group 17. My name is Yu Fai. Now I will talk about the introduction part and the model idea. This is the introduction. In 2014, Google Research proposed sequence-to-sequence network. And our idea is make sequence-to-sequence network to attention recognition. The core idea of the attention recognition is that the decoder use a directly connection to the decoder at each time step so that it can focus on parts of the source sequence. And this is the model part. And on the right side is the decoder encode framework. The encoder will encode the text to the vector, and then the decoder will decode the vector to the target language. And this is the attention model part. The attention model first appeared in the CV area and first used to solve the NLP problem in 2014. The most important part on this model is when the decoder is to assign more opposite part to the opposite part of the picture. And this is attention is different to other model has 2 points different. And this 2 points we can have a load. Now I pass to my group member to continue.
Hello, my name is Chu Min Hao. I will introduce the design part and the implementation of our group. First is the encoder. The encoder of sequence-to-sequence network is an RNA that outputs some value for every word from the input sentence. For every input word, the encoder outputs a vector and a hidden state, and use the hidden state for the next input words. We can see the structure and the code in the picture. Then it comes to the decoder. Attention allows the decoder network to focus on a different part of the encoder outputs for every step of the decoder's own output. First, we calculate a set of attention weights. This will be multiplied by the encoder output vectors to create a weighted combination. The result should contain information about the specific part of the input sequence, and thus help the decoder choose the right output words. The attention decoder calculating the attention weights is done with another feed-forward layer, using the decoder's input and hidden state as the inputs. Because there's a sentence of all sizes in the training data, to actually create and train this layer, we have to choose a maximum sentence length that it can apply to. Sentence of the maximum length will use all the attention weights, while shorter sentence will only use the first few. Then it comes to the implementation part. First, the data presentation design. We read text file and split it into lines and split lines into pairs. Then we normalize text filtered by length and content. Finally, we make word lists from sentence into pairs. In order to do the training, we need a variable to mark the words. We set a helper class called len to use as the inputs and targets of the next words later. It has words to index and index to words dictionaries, and a count of each word used to replace some rare words. Then is the training process design. We start the timer first and then initialize optimers and criterion. Then we create sets of training pairs. In the last, we start empty losses array for plotting. We use teacher forcing when we do the training. The teacher forcing is to use the real target outputs as each next input. Instead of using the decoder guess as the next input, using teacher forcing causes it to converge faster.
Hello, my name is Li Yixun. I will introduce 5 and 6 parts. At first, we train the model 75,000 times. We monitor and print the process statement for every 5,000 iterations. We can clearly see that the average loss decreases significantly with the increase of the training times. On the right side, it is a line chart about the loss value. After training, we randomly select 30 groups of sentences from the test data and conducted 5 such experiments. The average accuracy rate is 0.68. And for training model with iteration times 150 times, the accuracy rate rises to 0.87. A useful property of the attention mechanism, it is a highly interpretable outputs because it is used to weight specific encoder outputs of the input sequence. We can imagine looking where the network is focused most at each time step. Conclusion part is in this project, we built an English and to French machine translation by adding an attention mechanism to the sequence-to-sequence model and evaluated and visualized the results. We found that the natural network works better when we change the training times from 75,000 times to 150,000 times. We got lower loss and higher accuracy. For future improvement, we can increase the pooling degree of the corpus to reduce the training time or try with more layers, more hidden units, and more sentences. Compare the training time and results. Here is our reference. That's all for our presentation. Thank you for your watching.